I made a bunch of mistakes in my physics homework, so I wanted to go over a couple of interesting things I learned. One of those things was about toroids, the magnetic field inside of the toroid, and well, let's compare that to the magnetic field inside of maybe a solenoid over here, which would be something like mu naught I n divided by L. L is the length of the solenoid, but for the toroid, the loops actually go around here like this. I want to actually kind of like maybe make a note of this of some sort. These loops kind of go around here. Put this something like this. Maybe I could say so. These currents kind of loop around here in this type of way, and because of that, when we count these loops, we don't care about the length. We care about the circumference. Hopefully, this is the right direction. I think I did it kind of the opposite direction there, but I have time to use this, something like that. Okay, so we don't care about the length. The length isn't even involved in the toroid magnetic field here. So we only care about the average radius, which means we have to take R2 minus R1 divided by 2, and that's kind of what we can do to find the R average there. I might want to make a quick note of that. So R2 is R1 divided by 2. Okay. Something like this. That'd be slightly better. All right. And so that's kind of interesting. And so basically we've got the difference between that. So we use 2 pi average here. Just kind of updating my notes as I sort of figure things out here. And we can go back up. And I wanted to make sure that I also talk about the magnetic forces that kind of pop out of these things. Because say we have this there's a loop here, or we have this like this square loop, and we're sort of pulling it with our hand here. So there's actually some forces that pop up. If this was a conducting loop, you can see how like there'd be a force sort of like charge moving this way. So because of that, we can use QVB and we can sort of find we'll cross product there and find out the force this way. That's fine. But then we also have the idea that we can consider force being ILB. ILB is a good way to calculate force rather than QVB. Both of them will give you the same answer if done right. But this one's a little bit shorter. As you can see, we kind of already know the current, BLV over R, and this is because we know the I, this is induced voltage, like this. And so we can use the induced current and just say I L cross B, and so L is going to be this, and we're crossing it into B, which is a 90-degree angle, so we don't even need to worry about the sine component. So we can use this. That's pretty nice. And this is a key component here because I was trying to solve all my homework assignments using QVB, uh, and that became really difficult because things weren't working out very well. And so it was just easier to do it this way. And so it's kind of the interesting thing there. It's basically the majority of what I wanted to discuss. We can see how, like, this force over here is a positive force. Let's also consider that there might be a force this direction from the resistance So this is a resistive force here, and let's put it like this. So Fr, this one does sort of a is it Fr in the y direction, right? And it's negative. So this is like the resistance force here, and that's interesting there. And then of course we have in this force the hand points. We kind of have a balanced forces. We will have a constant velocity, and uh, and so because this force over here is negative from the B field, and because this force is positive and they actually happen to be the same, well, it turns out that the B field actually does not work, so that's kind of interesting. Uh, and the fact that if we don't even have the hand pulling here, and we just kind of give it an initial push there, we'll notice that this velocity here, it doesn't even remain constant, it does decay, and because this is decaying velocity, usually we would need time to go to infinity for this to fully decay. And so we can sort of replace v with this decay factor here, and that's kind of cool. So yeah, these are just some very interesting concepts that we are sort of thinking about. One last thing here is that when we're looking at power, we could also we should do an integral here if we're going from an initial time to final time, so we would be able to integrate the power integrals. So there we go. These cheat sheets that I'm making here, they're available on my website, and you can actually download a free sample at freephysicsmap.com. We got the original physics map. This is actually for magnetism, but we offer the mechanics one for physics one as a free